If I have a wall here, and let's say I'm holding the rope in my hand over here, let's just give this a distance. Let's say this is 1 meter away. And if I could generate one big wave, picture I shake my rope and I generate this one big wave, and the wave hits there. What is the wavelength of that wave? Well, I hope that you see that because we're at the same height here that we're at here, in theory, that wave would come over to here. So the wavelength would be 2 meters. Because we're only looking at half the wave. So let's erase that a little bit. What would happen to the wave if it hits the wall? I guess it doesn't matter which end the wall's at. It hits the wall, but it's fixed. What we learned in the last video was that when a wave hits a fixed point on the wall, it will reflect back on the bottom. We end up with this really neat pattern where it goes over on the top and back on the bottom. Usually this is done with some kind of machine that vibrates really quickly. And when it happens really, really fast, and you end up with this wave coming over and the wave coming back, it actually just looks like that. Well, it's a poor diagram. But we end up with this. It looks like there's the top and the bottom of the wave. And this is called a standing wave, because it looks like it's standing still. Okay? It's almost like a big giant skip rope, but you don't see any of the vibrations in here. We only see the vibration on the top and the bottom. And this is a standing wave. Remember, the key piece of this is that the wavelength is actually double of that because we didn't see the other half of the wave. Of course, we have to have some definitions. The place where the standing wave is meeting in the middle is referred to as a node. And the places at the top and the bottom are antinodes. Start. When you have one standing wave, we would call this n is 1. There's the number of standing waves is 1. This is what we would refer to this the standing wave of n is 1. It's what we would call our fundamental frequency. So when we've got this length, this wavelength here of 2 meters, that is the fundamental frequency of this wave. And we have other frequencies that would also work, and they're going to be referred to as overtones. Let's jump to a new screen here. So we can have n equal to 2. This is called an overtone. Once again, I've got my wall, and once again, 1 meter away. But this time what I'm going to have, instead of having one standing wave, I'm going to have a big wave we have exactly one wave here. What happens when it hits the wall? Well, we know that it's going to reflect, and it's going to reflect in the opposite direction. And we'll end up with this. Once again, when this vibrates at really high speeds, it looks like it's standing still. Once again, we see the top half of the wave on the left, the bottom part on the right, and then we see the top part of the right and the bottom part of the left. Once again, it looks like it's not moving. This one has 3 nodes. Okay, one here, one here, one here. And of course, it still has our antinodes here and here and here and up there. Wavelength here is 1 meter. Please note that the nodes occur half a wavelength apart. Okay, so in this example, we have 3 nodes, and each node is half a wavelength from the other one. These are all referred to as natural frequencies. Let's see if we can do natural frequency with 4 nodes. Once again, I've got my wall. This time, instead of stopping there, I'm going to go 1 more to there. Once again, this is 1 meter away, trying to keep the distance consistent. When it hits the wall, it reflects, comes down, the wave goes back up. Okay. Once again, we have a node here. We have a node here, a node here, and a node here. 4 nodes. This is our second overtone. We could also say that this is n equals 3 because we have 3 standing waves. A bass guitar, the string is approximately 32 inches or 80 centimeters long. For the first 4 fundamental frequencies, let's see what we can figure out. So the first question says, draw the string. Okay. So the first 4 fundamental frequencies. So the first one is going to look like this. It's our first standing wave. I'll draw the top part in green, and I'll do a dotted line on the reflection. So there's the first one. While I'm at it, let's draw the second and third and fourth. Okay. So the second one, I'm going to try and make them about the same length. There we are. Third one's going to and the fourth one. There we go. And I'll put the other end on here. Okay, so there's our first 4 fundamental frequencies. Next question says, find the wavelength. So the wavelength is how long does it take to go through one full cycle? Well, we know that these are, let's say, 80 centimeters apart from here to here. So let's look at each of these. This one is only half of a wave. We need to go all the way to here to get one wave. So the wavelength here is 2 times 80 centimeters or 160 centimeters. In the second one, we can see that the wavelength is exactly our length. So the wavelength here is simply 80 centimeters. Well, the third one, technically the first wave ends right there. So what I'm going to do is I see that I've got 3 different regions. So the wavelength here would be 80. I'm going to divide that by 3 and multiply it by 2. And that'll give us a wavelength of 53.3 centimeters. And the last one, hopefully you'll see that it goes through 4. I'm actually going to do it. I'm going to do it the same way. I'm going to take it. Okay, I'm going to divide that by 4. So divide that by 4. And I'm going to multiply by 2. And the reason I'm multiplying by 2 is I want to get through 2 of these humps here, one full wave. So that one I can do in my head here, 40 centimeters. Okay, so I've drawn it. I've got the wavelength. How many nodes and antinodes? Okay, the first one here has nodes and nodes. The first one has a node at the start and at the end. So there's 2. The antinodes, well, there's 1 there. And this one here is, it's essentially the same antinode. So I'm going to say there's 1 antinode there. It's in the same location of the wave. Nodes on this one, I have 3. Antinodes are here and here. There's 2. This one has 1, 2, 3, 4 nodes. And hopefully you see the pattern. There's 3 antinodes. And lastly, 1, 2, 3, 4, 5 nodes and 4 antinodes. And the last question was the number of standing waves. N, let's put it right here. N is 1. On the second one, N is 2. Third one, N is 3. And on the fourth one, N is 4. I hope what you notice from this is that the number of standing waves, which I'm calling N, is equal to the number of antinodes. And the number of nodes is equal to the number of waves, N plus 1. Here we go again. I have a guitar string, 82 centimeters long. It's given a pluck. The speed of the wave speed, 352 meters per second. And I want to know, I got the length here. I'll just call that L, 82 centimeters. And we want to know the frequency of the first 4 harmonics. Okay, so we'll talk more about that. Okay, so what we know is that we've got this 82 centimeters long, and we're going to assume that that's the first harmonic. Our first harmonic is this. So it's our first standing wave. N is 1. And we can use our speed format. Well, first of all, I need to know the wavelength. So the wavelength of that would be 82 centimeters times 2. That's going to be 1.64 meters. Okay. So next up, what we're going to do is I'm going to take my formula here for speed. And speed was lambda times f. So to find f, we'll have v over lambda. So our frequency here, our fundamental frequency, is going to be 352 meters per second over 1.64 meters. So our fundamental frequency, F, we're going to call it F1, that's our first one, is going to be 214.6 hertz. So that's our fundamental. What would the next one be? And here's a formula, nice easy formula. I'll put it in green so you can see it. The nth frequency is just going to be the number of standing waves times the fundamental frequency. So what does that mean? If I want to know the second one, F2, I just take my original of 214.6 hertz and multiply it by 2. And that's going to give us 429.3 hertz. There's some rounding here. I didn't go with the significant digits. F3 would be my third fundamental frequency. And that will equal 643.9. And my fourth fundamental frequency, we'll just take that first one and multiply it by 4. And I have 858.9. Oops. 0.5. Hertz. Okay, this time I'm given the fundamental frequency of the first harmonic. Okay, so F1 is 310 hertz. And the string, I see a length of the string here of 76 centimeters. Okay, what is the second and third harmonic? So what I'm looking for is, F2. Once again, F2 is just going to be 2 times 310 hertz. That's an easy one. I can do that in my head. That's 620. And F3 would be 3 times that number, which would be 930 hertz. So that was easy, part 1. Now we need the wavelength and the speed. Okay? Well, if this is the length of our first harmonic, remember this is this length here, and then gets reflected underneath. That wavelength will be 2 times the 76 centimeters. What's that going to give us? That's going to give us 1.52 meters. That's my wavelength in meters. Okay. What about my second one? Well, my second one, okay, we'll go there. Once again, I've got this reflection here. Well, this time my wavelength is simply 76 centimeters. That's the second one. I'll put a little 1, 2, and a 3 here to represent these. Third one, Once again, dot it under. Third one will be 2 times 76 divided by 3. And I'm calculating 50.66666, round that off to 7 centimeters. The last part of this question was to calculate the velocity of the wave. Now, the velocity of the wave is simply the wavelength times the frequency. Now the question is, which one should I use? I've got 3 frequencies and 3 wavelengths. Let's just do it here for a couple of them, just to see what we get. If I take number 1 and multiply it by frequency 1, wavelength 1, I will see that I have my first wavelength was 1.52 meters, and my first frequency is 310 hertz. And so the first one I'm going to get here is 471.2 meters per second. What would happen if I did that with the second one? Well, if I use V2, and my wavelength here is 0.76 meters, multiplied that by the second frequency, and what we're going to see is that we get the exact same answer. So when you want to find the speed of your string, or of the wave going down the string, it doesn't matter which wavelength and which frequency you use, as long as you use the one from the same harmonics.